Good day everyone, my name is Joseph. Welcome to our course, Mastering Machine Learning Algorithm. In this session, we will learn about a random variable and measurable function. At the end of our lesson, you are expected to identify the concept of random variables in the context of machine learning, appreciate the importance of random variables in the field of machine learning, and relate a measurable function to random variables. So every day, we make decisions. Unconsciously, it's almost every minute that we do it. And all the times, these decisions are based on the things that we observe and their chances of happening. So, for example, you would like to go shopping. However, it depends on whether or not it will rain. Of course, if it rains, you will not go. Accordingly, if it doesn't rain, you will. Maybe you will ask yourself, what is the tendency of raining and the tendency of not raining? Then you would try to go back to your memory of the weather conditions for the past few days and make some kind of assessments, because the data that you will have will make you make decisions. So basically, this is the gist of our lesson. So let's first refresh our memory of our high school or university lesson on random variables. I believe that your teacher was too good enough in teaching you about it. So you were taught that random variables are variables whose possible values are outcomes of a random phenomenon. Still remember? Or maybe you would like to ask me, what is a random phenomenon? Or what makes a variable a random phenomenon? Okay, well, the answer is just a plain one. It is called random or random phenomenon because we know exactly that the outcomes will occur, but we do not know which outcome will take place. First, second, third, and so on and so forth. So for example, this is just a very simple example. I have here 3 pens. So we have violet, we have the blue, then we have the orange. So I'm going to ask you to pick one at random. So let's imagine that you are blindfolded. So with this, we know that all of them have the same chance of being picked. But as to which one of them, we do not know yet. So this is the simple concept of a random phenomenon. A random variable has 2 properties. First, it conveys a result, and second, it is measurable. In the first property, we have to think of 2 processes. So let me write here. It is objective, then subjective. It is objective random process. It can also be a subjective random process. It is objective because we know that the outcomes are complete, meaning to say we already have the knowledge of all possible outcomes or results. Okay, now to the second process. Subjectivity deals with uncertainty. So it has something to do with uncertainty. It means that the outcomes are uncertain because of the incomplete information. So it means that there are some information that are missing. So an example of the first process, objective process, is tossing a coin. So definitely you know that we could have tail or head only. So these are the 2 outcomes and no more. An example of the second process is identifying the weight based on diet and height, and this is subjective because there are some missing informations. So there are 2 kinds of a random variable. It can be categorical, it can be numerical. So categorical variable has something to do with quality. This is why it is also called quantitative or qualitative. Let me write here. Qualitative. Qualitative. So, if you are asked about categorical variable, do not forget about qualitative, in short, quality. So the most essential concept about it is that it can take only one of the limited and usually fixed number of possible values. Don't forget, limited and fixed number of possible values. So for example, we have male and female. So you cannot be a male and at the same time a female in the strictest natural sense. So if you choose male, you can never be a female. If you choose, or if you are a female, you can never be a male. Another example is black and white. So let me write here, black and white. So obviously, if you choose black, then you cannot choose white, or if it is white, then it is not black. So make sense? Do you have some questions? So now let's go to the second kind. So this is called numerical. The root word of numerical is number. Obviously, it's very simple, which simply means quantity. So while categorical is qualitative or qualitative, numerical deals with quantity, so that therefore it is called quantitative. So let me write here, quantitative. So you can just ask yourself how much or how many. So these two questions would tell you about numbers. So what is interesting about numerical is that it can be discrete, it can also be continuous. So discrete simply means fixed. So you can just count the number of elements involved. So for example, you would like to know the number of persons in the house. So for you to do this is to ask yourself, how many persons are there in the house? And simply you can count 1, 2, 3, 4, 5, and so on and so forth. So there are fixed number of elements involved. So in the case of continuous, our question is just how. Right here. So how? Just like when you say, or just like when you ask a friend how tall he is. So he would simply tell you that he is 5 and 5'1" meters. And maybe you would ask me, does his height change? Of course, yes, of course. Unless when he is old enough that his growth hormones stop. Of course, growth abnormalities are set aside here. So as you can see, in continuous, there is a finite or infinite interval. So this interval can only be measured using a measuring tool. So for example, in the case of height, we use stadiometer or a tape measure will do. I'm so sure you have experienced that when you go to clinic or hospital, and usually the doctor would, or even the nurse would, get your height or even your weight. So far, if we're going to limit ourselves on this kind of a discussion, we will be able to skip delicate properties of a random variable. Maybe you would want to ask me, why? Why do we have to skip some of the delicate properties of a random variable? So again, the answer is simple. Talking about random variable alone is not very descriptive. So the best way to understand a random variable is to treat it as a measurable function. So let me write here, measurable function. And maybe you would ask me, Joseph, what is a measurable function? So a measurable function is a function that maps. The keyword here is map. Let me write here, map. Don't forget this word map. It maps the outcomes of an unpredictable process in numerical terms, often represented as a real number. So this definition sounds high. Please do not be intimidated. We're going to make it simpler. So to better understand this term, let's study the formal construction of probability by way of this very simple example. And this example has been repeated so many times. I'm so sure when you were in your high school or university you had this. So to better understand this term, let's study the formal construction of probability by way of this very simple example. So for example, you are asked to toss a fair die. I am so sure everybody knows what a fair die is. So obviously, there are 6 possible outcomes. So this can be written as the total set of possible outcomes. So because the die is fair, the probability of each outcome is 1 over 6. So as you could see here, we have 6 elements of a set. So 1, 2, 3, 4, 5, 6. These are the total possible outcomes of a fair die. So the first thing to do is that we are going to identify the measure of each set. So that is the set of 1, the set of 2, the set of 3, the set of 4, the set of 5, and the set of 6. So, and then let's show that each probability mass function is equal to each other. So as you could see here, the probability mass function of 1, this one, mass function of 1, is equal to that of 2, which is equal to that of 3, and so on and so forth until the probability mass function of 6. So and then we can, again, as what we said, we said that each of them has a probability of 1 over 6 because they have an equal chance of taking place. So here, let's show the map of one measurable function. So as you could see, this is the map of the measurable function of 1. I mean the probability function of 1, which is equal to 1. So this one shows a map of the set of 1. This. So still remember when I said that it is represented as a real number? So 1 is represented by 1 as a real number. So the set of 1 has only one element. So maybe you would want to ask me, why is it that 1 is only 1? So the answer is that it is because the set of 1 has only one element. So we will have a separate lesson on this topic. This topic is quite interesting and sometimes very elaborate. So our future lesson we will talk about this one more about the sets. Okay, so this is our number line. So as you can see, each number in our set is represented in this number line. So we have 1, 2, 3, 4, 5, and 6. So remember, we have 6 possible outcomes in a fair die. So only one value is represented by each number. So of course 1 is 1. Still remember. So here, so 1, there's only the set of 1 is 1, and going to 6, the set of 6 has only one value, which is 6. So they have equal weight. So it means to say that there are no overlapping properties. So when we say no overlapping properties, the property of 1 cannot be the property of the property of 1 cannot be the property of 2, and the property of 2 cannot be the property of 3, and so on and so forth. This is the meaning of non-overlapping properties. So this kind of map may not be that very interesting. So what about if you're going to go to a very more challenging situation? So here we're going to make things more interesting. So suppose you are asked to construct a fair coin from a fair die. So again, we are equating a fair coin and a fair die. So it means that you throw a die and record the outcomes as if you toss a fair coin. So, and then again, maybe you would like to ask me, how can this be made possible? So just like what we do in the first example, we are going to define a measurable function. So we have here two measurable functions. We have 1 and 2. So the set of 1, 2, and 3, and the set of 4, 5, and 6. So it means that if the die comes up 3 or less, 3, 2, or 1, it means that it is head. So if the die, or if a die comes out 4, 5, and 6, 4, 5, and 6, it means it is tail. So this creates two non-overlapping sets. Again, why non-overlapping? Because the elements of this set cannot be found in this set, and also the elements in this set cannot be found in this set. So because the elements, because the set have the same number of elements, we can therefore say that they have the same probability measure. So again, we have here 3 elements, and we have here 3 elements, so we can say that they have the same probability measure. So to speak, the probability mass function of 1, 2, and 3 has a probability measure of 1/2. Equally, the probability mass function of 4, 5, and 6 has a probability measure of 1/2. So they are the same. So at this point, maybe you would try to ask me, is this the only way to construct a fair coin experiment from a fair die? What do you think? Can you give me your answer now? Of course, the answer is absolutely no, because we can make alternative definition of a set. So let's try to look at this one. So for example, we can define a set like this. So we have a set of 1, set of 2, a set of 3, 4, 5, and 6. So it means to say that we can only consider 1 to mean head and 2 to mean tail. So this results to a probability measure of 1/2. This one, 1/2 for 1, and 1/2 for 2. And maybe you would ask me, what about this one? What about the set of 3, 4, 5, and 6? If you're going to toss a coin, and then when the result is 3, 4, 5, or 6, then what will happen? The answer is that these numbers, these outcomes, are disregarded. Why? Because we have alternatively defined the set, which could either be the set of 1 to mean head and the set of 2 to mean tail. So hence, for this set 3, 4, 5, and 6, the probability function of the set 3, 4, 5, and 6 has a probability measure of 0. So as you can see, this is somewhat wasteful, but this kind of solution really solves the problem. So I hope you see the interconnecting dots of theory which provide a framework to carry the notion of uncertainty. After our discussions, I expect you to ask me, why do we have to study this? This is the foundation of feature engineering, which will be taken up in our future lesson. This tells us how much information is preserved. So for prediction and neural networks, this is the foundation of understanding the likelihood of an outcome. So after all being said and done, let's try to evaluate ourselves. What is a random variable? Why is a random variable not very descriptive? Is there only one way to construct a fair die experiment? Why? Why not? I would really appreciate if you write your answers in the comment below. So do not forget to subscribe, like, and share. Please click the bell icon to be notified of our new session. See you in the next lesson.